In C, the standard string type is actually just a character array. There's no special type just for strings. So here we are assigning a string literal to a char pointer because the string is actually an array of chars. So when I dereference s+1, I'm getting the second char of that char array. Now you might assume that the string here, ABC, is an array of 3 chars, but in fact it is 4, because by convention in C, strings end with a null byte, a byte which has all the bits set to 0. In fact, all of the standard library functions in C that deal with strings expect strings to be in the form of a char array ending with a null byte, because the null byte signals the end of the string. So in fact there is a standard library function called strlen, as in string length, where you pass in the char pointer pointing to the beginning of the string, and it returns the length of the string, not including that null byte. So here strlen is going to return 3. So because the length of the string is effectively encoded in the string itself, we can just pass in a string to a function without having to also pass in the length itself. Now there are some problems with the way that C does strings. First off, the longer the string, the longer it takes to calculate the length of a string, because the strlen function has to start at the front and read through each byte until it finds the null byte. The other basic problem with these strings is that they are in ASCII, not Unicode. So if you want to support languages other than English and a few other Western European languages, you pretty much can't use these strings. To get Unicode strings, you would bring in some other library that implements them. Finally, it's important in C that you treat these string literals as if they are constant. That is, you shouldn't attempt to modify the bytes that make up the array that is that string literal. The reason is that you don't actually know where that array is in memory. Normally arrays that you declare inside a function are local to that function and they're just put in the stack frame of calls to that function. But the C standard allows compilers to treat string literals in a special way. Rather than put those character arrays on the stack, compilers might put them in a permanent place in the process. And if you have the same string literal in different places in your code, the compiler might decide to represent them with just one character array. So what might happen if you attempt to modify one of these strings is that you're going to be modifying it in one function and unexpectedly find that you've modified strings in other functions. So when you deal with string literals, treat those arrays as read-only. In C, a structure is a data type which you, the programmer, define yourself. And you create such a data type by composing it out of existing data types. To define a structure, we declare it starting with the struct keyword, and then we pick a name for this type we are defining, and then in curly braces we list the members, the data types which make up our struct type, and then we end with a semicolon. Once we've declared a struct type, we can declare a variable of that struct type by writing struct and then the type name and the name of the variable. Once we have a struct value, we need to get at the individual values that make it up. So we use the member operator. The member operator is a dot, and before the dot you put some expression that evaluates into the struct value, and then after the dot you specify the name of the member. So here let's first declare a struct type, which we will call cat, and the cat type will be composed of a char pointer named name and an int named age. Notice the members are written just like normal declarations, but they're inside the curly braces of the struct declaration. A struct type declaration can be written inside a function, but then it would only be visible inside that function. So normally we put our struct declarations outside of functions, and then it's visible to everything after in the program. Once we've declared our struct type, we can then declare variables of that type. So here we are declaring a variable named mittens of type struct cat, and just assume we're writing this somewhere inside a function. Once we have our struct cat variable, we can assign values to its individual members using the member operator. So here we write mittens.name and assign it a string, because remember name is a char pointer, and then we assign mittens.age the int value 5. Now let's say we have two struct variables, a struct cat called mittens and a struct cat called fluffy. If we assign fluffy to mittens, it is the same as if we were to assign fluffy.age to mittens.age and fluffy.name to mittens.name. It's the same as assigning all the members of one struct to the corresponding members of the other. The one other thing you can do with a struct variable is reference it, because in fact, for every struct type you define, there is a corresponding pointer of that type. So here we declare a struct cat pointer named p, and we assign it the address of Fluffy. You might expect that we should be able to use the equality operator with struct values, but for some arcane reason it's not allowed. We can not only create pointers to structs, we can also create arrays of structs. So here we're creating an array of 8 struct cats, and like with any other array, cats here is actually a pointer value. So if we dereference cats, we get the first struct cat in that array, and so we assign here its name member, the string Oscar, and then to assign a name to the second cat in the array, we dereference cats plus 1 rather than just cats. And if you're thinking this is ugly, you're right, it is ugly, but there's actually a prettier syntax which we'll introduce later that does the same thing. Finally, we'll note that the size of operator is particularly important when used with structs. Here we're allocating a block of memory for 8 struct cats, but without the size of operator we really couldn't do it. The problem is that compilers sometimes pad structs, so our cat is made up of 2 different members, age and name, but it's not necessarily the case that name comes immediately after age in memory, or vice versa. For the sake of platform-specific optimizations and efficiency concerns, the compiler might decide to put some bytes of padding in between, and then you would have no idea how big your struct is in bytes. Even if compilers didn't do this padding, it would be really inconvenient if we didn't have size of, because what would happen is that we would hard code the number of bytes we use per struct, but then we might actually change the struct definition. We might change one of the members to a different type, or we might add and remove members, and then we'd have to go through our code, and everywhere where we use the size of that struct we would have to change it. If we just use size of, we never have to do that.